Dear students, let us continue our video lectures on Advanced Digital Signal Processing course. Let me share the screen. In this video lecture, let us discuss on FIR filter design by windowing technique with little more details. In the previous video lecture, we have seen for the differences between the ideal and the practical filters, especially when we are given an input and we expect that the output has only certain frequencies of the input, and the certain frequencies in the input signal are to be attenuated. That is, we need a frequency selective filter, okay, that selectively passes some frequencies or selectively attenuates the rest of the frequencies. Okay, so what we have seen is the ideal filter response, okay, in the frequency domain looks something like this, especially for the low pass filter. Okay, and we have seen that the ideal filter in the time domain, okay, has an impulse response that extends from minus infinity to infinity. Fine. So this has a impulse response that extends from minus infinity to infinity, given by the roughly it is sinc function. Okay, so something like this. Okay, so however, for practical reasons, we cannot have h of n range extending from minus infinity to infinity. Second thing is, we wish the impulse response has to be causal for a realizable filter. That means h of n has to be less than 0 for n less than 0. Okay, for causal and realizable. Okay, filter. For that reason, as we discussed, we shift the desired impulse response. In fact, this is the desired impulse response, okay, to have a desired causal impulse response. Okay, so we generate from this a causal desired impulse response as h of n minus n naught. In fact, this n naught is equal to the half of the filter length. Okay, they are the impulse response length. So, and we have seen that this will enable us to have a most of the significant terms of this impulse response are the samples of the impulse response, okay, in the positive region, and hence this effectively changes the origin starting from probably something like this from here to m. Okay, and we still will not like for practical realizations, especially in finite impulse response filters, we need only finite samples to be taken. Okay, so for that we apply a window function. Okay, this window function in time domain will enable us, okay, to restrict the number of samples in hd of n. So the practical impulse response is hcd of n multiplied by w of n. Okay, w of n is obtained by a window function, okay, which will enable us to select only the samples from 0 to n m and 0 else. Okay, this is here we refer to as rectangular window. Fine. Because of this consequence, we have now the impulse response of the practical filter that we generate, okay, having Okay, 0 to m. These are the samples of h of n, okay, which are truncated with from hcd of n and also delayed version of hd of n. Okay, so given these samples as h of n, okay, what we wish to do is our practical filter now, which is h of e power j omega, okay, will be obtained as convolution of w e power j omega along with the hcd, okay, desired impulse response e power j omega, right? And this convolution is see in the frequency domain, and you can see that this implies, so we have here, so this is, okay, you can see that this is convolution of the ideal filter, okay, with the window function, Fourier transform of the window function, which is also a sinc function because the window function we have taken here is a rectangular function. Okay, this is w e power j omega, and this is h cd of e power j omega. We have here a phase term in hcd. Okay, convolution of these two will enable us to have a practical filter which will be somewhat looking like this. Okay, somewhat looks like this. And as we said, the practical filter is not just defined by the cutoff frequency, and like in the ideal filter, this is the ideal filter. Okay, it is also defined by the attenuation in the pass band, 1 minus delta p and 1 plus delta p. That is, ripples in the pass band will come because of the like the ripples of the window function. Okay, so please note that these are the ripples of the window function. Okay, and these are the stop band ripples also comes because of the ripples of the window function, delta s. So the attenuation we ideally wish to have is 1 plus or minus delta p in the pass band. Okay, and the ripple, we can allowable ripple of delta s, okay, in stop band. Okay, in stop band. Fine, and we hence these are the specifications. Okay, we give delta p, delta s, and we also denote the corresponding like where the transition happens between the pass band to the stop band or stop band to the pass band. Okay, we consider this as transition band. That means sharply we may not be able to go from the stop band to the pass band or pass band to the stop band, unlike in ideal filters. And because of this main lobe width, uh, which is not narrow enough to make this transition sharp, we will have some transition band. Please note that if this was the impulse function, then ideally we would be getting a ideal response. Since this is not narrow as impulse function, we will have a transition band, and hence this corresponds to will this results in, okay, this width results in transition band. Okay, so and this is because of the main lobe width. Fine, and this is the transition band, WP to WS. So delta W, which is the transition bandwidth, okay, is this. This is proportional to main lobe width. Of window function. And delta P and delta S ripples are proportional to the relative height of side lobes. Okay, with respect to main lobe. Okay, so let us see these details in more detail. Okay, more clearly, and also see, is the rectangular function alone is a possible window function, or are there any better ways of windowing, okay, or extracting the finite number of samples from the infinite impulse, desired impulse response, to get the finite impulse response for practical realization. Okay, these things let us see now. Okay, hope this is clear. So we have here, this is what we are doing here is discrete time Fourier transform. Okay, in fact, this is inverse discrete time Fourier transform. And you have got this, and from this process is referred to as windowing. Again, all this process that we are writing here is, okay, is windowing. Okay, bringing causality, and then this is windowing. Okay, this process is windowing. And then you got the shifted or the like delayed, and then the finite impulse response. So this is again what we are taking here is discrete time Fourier transform. Okay, for the time domain operations we have done here. Okay. H of n is what we are sketching here. Okay, these samples corresponds to H of n. Fine. So now let us see these details in more. So please see here what we are doing, what we discussed in the previous slide is more summarized here. So you can see that this is the Fourier transform of the window function. When we do convolution of Fourier transform of the window function with respect to the ideal frequency response, what we get is this. Here you can see very clearly, whenever there is a overlap of the main lobe with respect to the pass band, you see that roughly pass band magnitude comes with ripple in pass band that is attributed to the peak due to the side lobes. Okay, as we discussed, this is referred to as main lobe and this is referred to as side lobes. In case the height of side lobes is higher, the ripples will be higher, either in passband or in stopband. Okay, and the how fast we move from the passband to stopband depends upon the width of this. If this is too narrow, then what will happen? We very sharply fall off from passband to stopband. Whereas if this is wider, we slowly transit from the passband to the stopband, and hence the transition bandwidth, which is referred to as the pass band, this up to where you get the magnitude of the frequency response greater than 1 minus delta p is referred to as pass band. Below the frequency response having the magnitude less than delta s is referred to as stop band. Okay, as per the definition, what we see is, okay, the pass band is band where mod h of e power j omega, okay, is greater than or equal to 1 minus delta p. Okay, whereas stop band is the band where mod h of e power j omega is less than or equal to delta s. Okay, so here you can see that the up to here you can see, okay, up to here you can see that the it is 1 minus delta s if we consider. Okay, then up to here you have above 1 minus delta s, and this is the cutoff frequency of the passband, and this you can consider in some sense delta, sorry, this is delta p, delta s. Then below say delta omega s is the cutoff frequency, okay, of the stop band. That means stop band is the band for all omega, okay, uh, less than or equal to omega s. Okay, such that the where you especially said the magnitude response is less than or equal to delta s, that is stop band. Okay, this is stop band. Fine. Here in between these two pass band and stop band, what we have is the transition band. Okay, so please note that the spectrum is symmetric. So if we understand from 0 to pi, same thing will happen in the other direction. So we don't really bother much on the other direction. Okay, on negative direction. Fine, that's why we are everywhere denoting as mod, so that actually in either side it is taken care of. Okay, so the ripples, essentially the understanding from this figure we get is the transition band, okay, is due to the main lobe width. Okay, main lobe width is what determines the transition band, width of the transition band, and whereas the ripples are, okay, because of the height of the side lobes. Ripples to side lobe heights. Okay, so ideally if we consider this w e power j omega, okay, to be an impulse function, fine, then what does happen? There is the main lobe width is 0, is equal to 0, and then the side lobes height is also equal to 0. Okay, these two imply that, this implies that, okay, no transition band, sharp transition and whereas this implies that, okay, no ripples. But getting this is ideal case, ideal window function, okay, in frequency domain. If we need to have this ideal window in frequency domain, what does it indicate? It implies that h of n is equal to 1 for all n. Okay, so which is not feasible. That means we consider, so w of n, w of n is 1 for all n. That means we are not windowing at all. We are taking all samples into consideration, and which is not feasible. So no windowing as such. Okay, so it is a ruled out case for converting or for getting the finite impulse response filter. Okay, so but however, thus in many of the practical scenarios, we need to make a compromise between the length of the window, that is m, okay, the length of the window and the shape of the window as well. We will see. Because as we have seen, for a rectangular window, you see that the transition bandwidth is like this. If we change the rectangular window to other kind of window, do we get any advantage, especially in terms of smoothly tapering off the time domain response of the desired filter? And will that have a consequence in terms of reducing the ripples? Okay, we will see that. Okay, so this is because as we have noticed, these practical in practical scenarios, we will not be able to exactly get the transition band to be 0, or we cannot avoid the ripples. Okay, especially when we do like finite impulse response filters for generating or designing the filter. So as we discussed, so we define transition band. Okay, we also define the stop band and pass band for the low pass filter. And we, as we denoted, the specifications are given not just in terms of the cutoff frequency, we give the specifications in terms of, okay, cutoff frequency for stop band, pass band, and then at respect to attenuations. So please note that now specifications for analog filter are omega p, omega s, okay, and then delta 1 means delta p and delta s. Okay, so whereas for the digital filter, as we have seen before, this is omega p, omega s, delta p, and delta s. And the relation between these two is omega p is equal to omega p into capital T, sorry, by capital T, or omega p into T equal to omega p. Omega p is equal to omega p into capital omega p into T. Similarly, omega s is equal to capital, sorry, omega s is equal to capital omega s into T. Okay, so and then delta p delta s remains same. So here please note that uh, delta 1 is delta, yeah, 1 is equal to delta p equal to delta s. Okay, so now transition band, as we have seen, is delta s minus delta p. So this is the same discussion that we had. Depending upon the window function we consider, the frequency response of the window function will have main lobes and side lobes. Okay, and we will see here more clearly what is for a rectangular window, how do they mm, look like and how do they affect. So we have seen for the rectangular window function is defined as 1 for m plus 1 samples and 0 else. This in frequency domain will give rise to okay, and this is plotted here. Plot of this can be observed here. As you can see here, based on this, the main lobe width is how much? Minus 2 pi by m plus 1 to 2 pi by m plus 1. Okay, so the main lobe width is this 4 pi by m plus 1. This is one of the very important factor because as we discussed before, this determines the transition band. Okay, this is in fact equal to delta W transition band. Okay, for all the practical reasons or design purposes, we use this relation for calculating or relating the length of the window that is required for designing a for the given specifications. So WS, WP are given specifications. Okay, that determine M. Okay, or M plus 1 length of window function or the impulse response itself. Okay, so this relation is the key for identifying how much should be the window length I should consider for designing a filter. Okay. Other important aspect to discuss here is for a rectangular window, you can see that, see if I increase this M, okay, what may happen is this filter, like if I increase M for a rectangular filter, okay, this will become more wider in time domain and hence this becomes more narrower in the frequency domain. Because of that, 4 pi by M plus 1 will become smaller and hence the transition band gets reduced. So the implication of increasing the filter length, that is if M is increased, imply that, okay, the transition band becomes narrow. Okay, this is an important or it is an advantage in terms of sharp transition from pass band to stop band. However, what will happen? See, there is a one phenomena referred to as Gibbs phenomena. What it says is the ratio of the main lobe height to the side lobe height is roughly fixed. That means if we decrease the width here, it increases the height of the signal because the energy in time domain and frequency domain is preserved. So if we decrease this, it increases the height of the uh, peak, and this also increases the height of the side lobes. So this in turn, this what will happen? This in turn, okay, increases this increases the peak of side lobes. Okay, peak heights of the side lobes. So if side lobe height is increased, what is the problem? It increases the ripples. That means meeting delta P and say meeting delta S and delta P increases. Okay, so meeting the specifications of delta S and delta P becomes difficult. So if we start with the specifications of delta WS and so if we start with the specifications of WS and WP, okay, and we end up with, okay, if we want the gap between WS and WP to is small, fine, then it ends up with higher values of WS, delta S and delta P. So there is a compromise that is needed between the decreasing the transition bandwidth and decreasing the ripples. So at the same time, we will not be able to have, okay, the filter or designed through windowing with lesser transition bandwidth and lesser ripples. Okay, so this puts up a challenge, or this puts up a difficulty. Okay, this implies filter design with low transition width band and lower ripples is challenging. Okay, so this puts up, so both are like, in if we decrease the transition bandwidth, then if we reduce the transition bandwidth, it increases the ripple. If we lesser, if we want more lesser ripple, then we have to compromise on the transition bandwidth. Okay, so both are in some sense like dependent on one another, and there is a compromise needed in the design of filters. One technique people use, okay, so with rectangular filter, now what will happen is, whatever we increase, we will not be able to decrease the peak amplitude height with respect to the peak of the main lobe. So what we do is, the other option is, rather than increasing the length of the filter, can we change the shape of the filter? See, what we have here is a rectangular filter, okay, which is having a in time domain, what we have is a rectangular filter. Okay, so it's the filter is like this. Okay, starting from 0 to M, and this is the discrete filter, please note. Okay, even though I have sketched it on a continuous plot. Okay, so this W of N, now the question is, this W of N is looking like a rectangular shape. Okay, so this is abruptly cutting the impulse response of the ideal filter. While designing, H of N is obtained through HCD of desired impulse response multiplied by this window. The question here is, instead of abrupt, because of this abrupt cut in the time domain, okay, there is a larger transition in the frequency domain. Okay, or there are like, there are more ripples in the frequency domain, more importantly. Okay, so to reduce the ripples, what we can do is, instead of having an abrupt cut in the time domain, can we have some kind of window functions which are smooth, rather than this like sharp cut like a rectangular window? The answer is yes. Okay, so we usually design with different window functions which are like, which doesn't cut sharply, okay, while they smoothly transit or smoothly smoothly multiply with a smooth function to have only few coefficients in the impulse response. So the same facts that we have discussed before are more elegantly shown here. So the transition bandwidth here, delta W, is WP and WS. Okay, WS minus WP. And since usually we are given with the continuous time specifications, what we should do is omega S minus omega P, okay, by capital T. Sampling time to get transition bandwidth. And this will determine the filter, like the length of the FIR filter or the window function. For rectangular window, it is 4 pi by m plus 1. Okay, so this is only for rectangular window. As we said before, there are other windows other than the rectangular window as well. Okay, right. So, and as we increase m, then as we said, then this becomes narrow and the transition band will be narrower. But at the same time, the ripple will increase. If we decrease this, if we increase this m, this becomes narrow, but the ripple will increase because the height of this also will increase. Okay. So, as we said, these ripples okay, and as we said, the ratio of the peak of side main lobe and the side lobe is roughly constant for a given window shape. Okay, for a rectangular window. So for given window, the relative height of main lobe peak to side lobe constant. Okay, so both will increase, meaning if one increases, the other will also increase. This is referred to as Gibbs phenomena. So what does it mean? By if you want to reduce the relative height of the side lobes with respect to the main lobe, you cannot take the same window again. Okay, the shape of the window has to be changed to make a better compromise. Of ripples for same m, okay, same length, window shape has to be changed. Okay, This third point, side lobe heights are proportional to ripples. Thus, if we, without changing the M, if we want to have a better filter, so fixing M, if we wish to have, if we lower, okay, ripples, okay, at delta S comma delta S, okay, what we need is to have a better window function. Identify so how people have extensively experimented on different window functions other than the rectangular window that we have seen before, okay, which is defined as we have triangular window, which is defined as n by m, okay, to n by m for 0 less than or equal to n less than or equal to m by 2. That means it reaches at m by 2 one value of 1 and is equal to 2 minus 2n by m for n greater than or equal to m by 2 greater than or equal to m. Okay, this is a rectangular window. Similarly, we have other windows defined. Rectangular window, one kind of window, triangular window. That means instead of like exactly truncating m samples, we taper off the m samples with this window. Okay, triangular window. The other window is other well-known windows are Hamming window, Hanning window, Hanning window. As you can see, these windows are motivated to taper off smoothly the impulse response quotients. So what we are doing is we are doing dot star of this with respect to h d of n. Okay, hcd of n. So I will write probably as a separate expression. What to get the practical impulse response? What we are doing is h desired impulse response multiplied by, in fact, dot star with w of n. Okay, so rectangular window suddenly tapers off like this, whereas triangular window multiplies like this. Okay, whereas the other windows, Hanning, and Blackman windows, they try to smoothly taper off the time domain impulse response quotients. Okay, so because of this, what we can do is the ripples will be small even for the same value of n. Okay, and the transition width may be slightly higher. So let us write the Hamming window. It is defined as Hamming window is defined as W of n is equal to 0.5 minus 0.5 cos 2 pi n by m for 0 less than equal to n less than equal to m, 0 else. Okay, similarly, Hamming window, it is necessary to remember these windows Because if we are asked to design a filter, what we should do is we first need to find the desired impulse response, HD of n. Okay, after finding this HD of n, the first step is to find HD of n. After finding HD of n, we should multiply with W of n to get H of n. Okay, Hamming window is defined as W of n is equal to 0.54 minus 0.46 cos 2 pi n by m. Okay, 0 less than equal to n less than equal to m, and 0 else. Okay, we have another window referred to as Blackman window. That is W of n is equal to 0.42 0.5 cos 2 pi n by m plus 0.08 cos 4 pi n by m. Okay, for 0 less than equal to n less than equal to m, and 0 else. Okay, this is more smoother. So as you can see, this is the this is the Blackman window, which is quite which has the more slope, more smoother. Okay, more degrees of freedom. This is Blackman window. Okay, whereas this is Bartlett window and triangular window are same. Okay, right. So as I said, if we wish to design a filter, what we first do is to get HCD of n, okay, and then find W of n, pick one of the W of n, and then find the H of n. Okay, with this we design a filter either in time domain or in frequency domain. Okay, so you can see now the comparison of these like respective window functions in terms of the main lobe width. Okay, that determines the transition band and the height of relative height of main lobe to side lobes. As you can see here, the main lobe width is maximum, okay, for rectangular window. This implies that, okay, this will have, sorry, this is minimum for rectangular window, indicates that this gives, okay, narrow transition band. Among all window functions. With same m. That is, if you fix m equal to 20, okay, and find out the transition bandwidths with rectangular filter, rectangular window, delta W with say Bartlett window, okay, for the same m, delta W with the say Hamming, okay, and so on. We can see that the delta W for rectangular window, that is transition width for the design with the rectangular window, will be lesser than the transition bandwidth of the, okay, triangular window is still less than of Hamming window and is still less than Blackman window. Okay, so for a given m, you can see that the width of the transition band, because the main lobe width is smaller, for rectangular window, it indicates that the transition band width is also smaller. Okay, as it is proportional to main lobe width. Whereas you can see that this is one point. Okay, other important point to note here is the relative peak of the side lobe with respect to the main lobe. You can see that the rectangular window, so if you see, I am just plotting the spectrum. Okay, assume that this is for the rectangular window. Okay, so you can see that from here to here, okay, from here to here, okay, it is only minus 13 dB. Okay, 13 dB lower compared to the main lobe peak to the side lobe peak. This for rectangular window. What is that I'm plotting here? I'm plotting the frequency spectrum. Okay, W e power j omega. Okay, for rectangular window. Whereas if I sketch it for another window, say for example, let us for Hamming window. Okay, you can see that. Okay, so this relative height, you can see that this is minus 41 dB down. Okay, so this is for the Hamming window. So which will have a lesser ripple now? The Hamming window for given m, and hence for the given m, that means given window width, for given m again. Okay, this is all also for given m. M, say the ripples, rectangular window has highest ripples because the side lobe heights are higher. Rectangular window ripple, I will say delta for rectangular is higher than delta for, okay, Hamming is higher than delta for Blackman. Okay, as you can see, if this smoothly tapers off, the ripples will reduce. Okay, so having higher ripple is beneficial, or the lower ripple? Having lower ripple is beneficial because uh, we can have lesser attenuations. Okay, and they more closely look like the ideal responses, filter responses. Okay, they does not deviate from the filter response. Delta is the deviation from the filter response in frequency domain. Okay, so say now if we are asked to design a filter, what are all these steps? So I will give a small example for the design of a filter. Design low pass filter. Okay, low pass filter with, say, rectangular filter, rectangular window. Second, with, say, Hamming window. Having window width m is equal to 10. Okay, so what do we mean? the low pass filter is e power j omega. Causal low pass filter is given by e power j omega m by 2. Okay, for 0 less than or equal to n less than or equal to m by 2, m and 0 else. This is the causal low pass filter, and corresponding h of n, hc of n, desired causal desired response is sine omega c. Okay, sorry, this is for in the frequency domain. This is we are defining in less than or equal to omega c. Okay, 0 else. So here omega c into n minus m by 2 by pi times n minus m by 2. Okay, this is the desired causal impulse response. Okay, if you sketch it, it starts from 0. Sorry, it extends from minus infinity to infinity, but the peak of this impulse response is at m by 2. Okay, to make a FIR filtered realization, that is finite impulse response, what we do is we need to multiply this with the window function. Here where the discussion on what kind of window we should use comes. So the practical impulse response or the finite impulse response, okay, by windowing. It comes through windowing. Okay, otherwise we will not get the finite impulse response. How do we get? Multiply it with W of n. Okay. Say now if you take the first problem, W of n is given by 1 for rectangular window, 0 to m, 0 else. Okay, and hence h of n is equal to sine omega c n minus m by 2 by pi into n minus m by 2 for n less than equal to m. Okay, here comes the range because now this is finite. Okay, and this is the like impulse response of the filter we have now, and this is a causal filter because it is ranging from only n greater than 0 or equal to 0, and this also gives the input output relationship as y of n equal to x of n convolved with this h of n. Okay, so you can easily denote with x of n, okay, plus x of n minus 1 into h of 1, okay, and so on. Okay, I'm not writing this explicitly here, okay, into h of 0. So if you do convolution, you can write this in terms of the x and h. Okay, so it essentially x of n into h of 0 plus x of n minus 1 into h of 1, okay, and so on. Okay, you can write like this. So this comes as a difference equation when we write especially as the input output relationship. This can also be looked in the frequency domain to see that y of e power j omega is equal to x of e power j omega into the filter impulse response h of e power j omega. Okay, so all this can be done given that we designed already the filter. So designing filter means getting this impulse response. This itself is the filter. Okay, or designed filter. Just getting this h of n is designing the filter. Please note that. And in the second example now, what we take? The Wn, the second example, Okay. The second example, we have Wn is corresponding to Hamming window. Okay, we substitute exactly this in the same expression. So this expression is common. Okay, h of n equal to Wn into is common. Okay, in this we substitute. This is the final expression for our substitutions. Okay. In some cases, we may not define explicitly which window to use, but we may define what attenuation should we have. Okay, in this pass band or stop band. If we specify that we cannot get the attenuation lesser than 31 dB, okay, either in pass band or in stop band, it means that we should use Hanning window. Okay, no other window we can use, right? So if the problem itself defines the attenuation in stop band and pass band, in the specifications, that itself gives the information of the window type. Okay, otherwise the usually the length of the window is given. So in the definition of the problem, we will have either the length of window given or the attenuations given for identifying the kind of window type, and then based on this we use the expression, that is the multiplication with the window function and the desired impulse response to design the filter impulse response. Thank you.